Today's podcast will cover information found in Exhibit P1 on the second floor of the University of Michigan's Exhibit Museum of Natural History. What you will find in that exhibit is information about the elephant and its ancestors, including the mastodon, whose skeleton can be seen on display to the right of the exhibit. The elephant is an animal that has fascinated humans and scientists for centuries. It is certainly a unique animal with its huge size, distinctive skin type, giant tusks, and distinguishing trunk. The trunk, or proboscis, is perhaps one of the most interesting anatomical features of the greatest of all land animals. However, the ancestors of the elephant did not always have this characteristic feature. Rather, it evolved to become the way it is today. The evolution of the elephant trunk shows why it was developed due to natural selection through the centuries and how practically useful it is to elephants today. Before understanding the evolution of the trunk, however, it is necessary to understand what the trunk is and what it is used for. The proboscis is a combination of the upper lip and an elongated nose. The trunk is a vital appendage to elephants. It is involved in eating, drinking, breathing, and many other tasks they perform. It can be used much in the same way as the human hand, for grasping things, reaching for objects in high places, and even for greeting other elephants. The Encyclopedia Britannica has stated that this trunk shake can be compared to a human handshake in that it may be associated with similar functions such as assurance and greeting, or as a way of assessing strength. All of these tasks are accomplished because of a complex system of muscle fascicles that enable the proboscis to complete small movements like picking up a flat object from the floor, or larger and more aggressive movements like ripping off tree branches. Due to the complexity and sensitivity of the proboscis, a severely injured trunk makes it virtually impossible for an elephant to survive. How did this appendage develop, though? The most primitive ancestors of elephants in fact lacked this feature, and some of these earliest ancestors did not have more than an elongated upper lip, where the modern elephant currently has its trunk. J. Morwood Dowsett states that the earliest, now extinct ancestors to the elephant had an elongated head and snout, which was developed through forcing its head under the banks of rivers for vegetation and roots upon which it lived. It is clear to see how natural selection would favor those with longer snouts so they could more easily find food. The individuals with larger heads and noses would survive and pass this trait on to their offspring, who would then continue the trend. Two ancestors to the elephant, vital in the development of the trunk, were the genus Phosphatherium and the genus Moeritherium from the Paleocene and Eocene epochs respectively. Moeritherium can be seen at the bottom left of the exhibit. These were the first to be categorized as belonging to the order Proboscidea, the order to which the modern elephant also belongs. Neither had a fully developed trunk yet, but rather they had a mobile upper lip like that of a modern tapir. They probably only stood about a meter tall, so they would have had to reach their heads and mouths in order to obtain their food sources. Natural selection over the ensuing centuries would eventually lead those individuals with larger heads and longer jaws to succeed so that they could reach their food more easily. The elephant's ancestors continued to have larger heads and elongated mandibles while also developing a shortened version of the trunk. As the head became larger, it became more cumbersome to hold up, but its increased size was still necessary in order to locate and obtain vegetation. This problem was eventually solved, and as scientist Hezi Shoshani has stated, natural selection provided the evolutionary answer. Over the generations, the head and jaws became shorter, and the snout, combined with the upper lip, became a long, flexible proboscis. An anatomical combination occurred that allowed the ancestors of the elephant to survive. The jaw became smaller, and tusks developed to decrease the mechanical problem of holding the head up, while the beginning of the proboscis slowly became longer to allow the animals to reach both high and low vegetation for survival. Evidence of this growing trunk comes from fossils showing an enlarging infraorbital canal, the opening that allows nerves and blood vessels to pass through to the trunk, and the location of the muscle structures that lead to the trunk. These are unique markings in elephant ancestors because the infraorbital canals, which are large in proboscideans, are small in other mammals. Also, the muscle groups leading to the trunk are located at an attachment that is higher and more posterior than in other animals. Miocene skulls also suggest that by that point in time, the trunk had become larger and had come to be situated more closely to where it currently rests in modern elephants, approximately between and above the eyes. This evidence also shows how the trunk was gradually moving from its lower position and shorter length to enable more efficient vegetation. Ancestors such as Dinotherium, which actually had lower rather than upper tusks, supported this more recognizable version of the proboscis. Dinotherium can be seen at the upper left side of the exhibit. Another aspect of the trunk also developed throughout this time, the finger-like tip that enables modern elephants to complete small tasks and grip objects. This part is actually different in the two surviving species of elephant. The African elephant has two of these projections, while the Asian elephant only has one. This distinct characteristic in the two species suggests that there was some kind of division in the evolutionary process that caused the African and Asian elephants to evolve from slightly different recent ancestors. Evidence has been found in frozen woolly mammoths that some of them had an upper projection similar to the finger-like projections on modern elephants. Again, the development of this flap was useful for vegetation because the mammoths would have been able to grasp grasses or flowers in order to eat in a way similar to Asian elephants. The similarity between how Asian elephants and their extinct relatives used their trunk tip demonstrates the evolutionary link between the two. Scientists have investigated the extent of the relation between modern elephants and mammoths. With mitochondrial genome sequences from 2 African elephants, 2 Asian elephants, and 2 woolly mammoths, all of which have been previously sequenced, they show that mammoths are more closely related to Asian than to African elephants. The modern African elephant thus diverged from the line that included the woolly mammoths and the Asian elephant, allowing for the development of their second projection, while the line that included the Asian elephant maintained just one tip projection. However, both species still do maintain the use of their unique trunk tips for obtaining their food source, among its other uses. In conclusion, the members of the order Proboscidea gradually developed the unique appendage that is the trunk, which the 2 remaining modern species have in order to more efficiently obtain their food sources and survive. The process of natural selection allowed the evolution of a head that would make seeking vegetation less cumbersome through the centuries, and the joining of the nose and upper lip created one of the most fascinating and useful anatomical parts of any mammal. Though many ancestors of the modern elephants have become extinct, the 2 that remain show the culmination of all these evolutionary processes. It seems that the key to the survival of these 2 species lies with their trunk. After all, severe trunk injury is often fatal. The natural selection involved in the development of the trunk has probably been one of the contributing factors to why the Asian and African elephants are the last 2 remaining species of the proboscideans.